This is problem 341, page 115. Ropes A, B, and BC are two of the ropes used to support a tent. The two ropes are attached to a stake at B. If the tension in rope AB is 540 newtons, determine the angle between rope AB at the stake and the stake, and B, the projection on the stake of the force exerted by rope AB at point B. Okay. So it looks like the stake has some position angle as well. All right, so I won't draw it because it's there in the book, and I think I would just confuse the matter by drawing it. So you'll just have to look. If we want the angle, so part A is the angle between rope AB and the stake. Well, we're going to need vectors for AB and for the stake. And it looks like they've already given us an XYZ coordinate system. So help me write down the vector R. And we'll use the book's notation, but I'm going to use the other notation as well. D with respect to B, or in other words, R from B to D. Okay. Help me write down the components of this vector. How would they go? Excuse me. Looks like we've got a negative x component. Does everybody see that? How much negative x component do we have?
1 meter.
Don't think so. Think of a, remember we're dealing with a stake. There's a zoom in part for the stake.
Meters.
0.08. Negative 0.08, right? Because see how from B to D, think of an arrow going from B to D. It's leaning back away from the x-axis. See that? B is in front of D in terms of the x-axis. How about B to D in the z direction? Well, let's go with y first. What would that be? Look at the stake drawing. I think it's 0.38 meters, isn't it? So plus 0.38 J. I'm not going to give you this one. Tell me the z direction. How much is it?
0.16.
0.16. Is that positive or negative?
That's negative.
Positive. It's positive. Because it goes from B to D, right? So it's moving along the positive z direction. So plus.
Oh yeah, you're right.
So 0.16. The units of all of these things are just meters. If we want to find the angle between that stake and a rope, what sort of principle are we going to apply? We learned about dot products, cross products. Which one do you think we're going to use?
Dot product.
The dot product, because the dot product is the one where you can take the magnitude of the two vectors times the cosine of theta, and that will give the angle between the two vectors. And that's the same thing as the dot product of the two vectors with each other. So what I'll need to do is also make a position vector from, let's see, which rope do we care about? AB. So I will need a rope from B to A. How would I write that in the book's terminology?
Negative 3 meters.
A with respect to B. From B to A. Right? So now about the negative 3 meters, which axis is that negative 3 meters on?
Is that X?
I don't think it's X. Oh, no, never mind. I see what you're doing. Yeah, I think you're right. It is negative 3 in the X direction. From B to A, yeah. Yeah, you're right. Yep. Negative 3I. Good. What's next?
For y, that would be positive 3.
Good. Plus 3J. Somebody else give me K.
Why not?
What is that?
K is positive 1.5.
It's from B to A.
It's negative 1.5.
Negative
Oh, it's
1.5.
negative.
See that?
Right.
Okay. These are also meters. The first thing that they wanted us to do is find the angle between these two. So all we need to do is realize that the dot product, and notice it doesn't matter what the order is. We can take D with respect to B dotted with A with respect to B, that's fine, or we could take the order the other way around, and we would still get the magnitude of D with respect to B times the magnitude of A with respect to B times the cosine of the angle theta between those two vectors. Okay, go ahead.
So when you're doing these problems, are you doing them in the most like timely manner, but not in that sense of more just like doing all that's necessary, but not doing like.
Am I always 100% efficient? No. On this one, am I being efficient? Yes, because I think this is the only way to go. I don't always think of the best way to do things necessarily.
Yeah.
Quite frankly, I'd probably just draw it in SOLIDWORKS if I really wanted this. But
And
you gotta
also
learn one.
that is a multiplication symbol between R.
Yeah, you gotta know the context. I tried to make this one bigger and that one smaller, sorry.
It works.
They're gonna be a little confusing. But because we've got two, look at this. This is a scalar and a scalar. It doesn't make sense to have a dot product with two scalars. This is a vector and a vector. It doesn't make sense to have multiplication with two vectors. You can't multiply, you can't times two vectors together. You have to either take the dot product or the cross product.
And why doesn't it make sense to have a dot product?
Because
with two
these are
scalars?
magnitudes, these are scalars.
Uh-huh.
So these are just numbers. There's no such thing as the dot product of two numbers. Good questions. Anything else? Okay, so let's calculate the magnitudes of some of these things. How will we do that?
That's gonna be,
Is it Pythagoras theorem?
Pythagorean theorem, good.
So I squared plus j squared.
Not I squared, the
Well, that's
multiplier
what
on
I meant.
I,
That's what I meant.
right?
That's what-
All right, and the same thing for the other one, right? So R A with respect to B, root -3 squared plus 3 squared plus -1.5 squared. You guys don't mind to calculate this for me, I'd appreciate it. I'll give you the first bit here, that's 18. I don't know what 1.5 squared is. Oh, yeah, I do, it's 2.25. So that's square root of 20.25, right? Whatever that is. Can't do square roots in my head very easily.
Square root of 20.25 is 4.5.
It's just 4.5?
Mm-hmm.
20.25.
To 0.25,
Yes.
the square root of it is 4.5.
Okay. I'm surprised. I believe you though. How about the other magnitude? What's it? They must have set up the problem so it come out nice and round like that. I bet the tent peg does too. Yeah, the length of that's what this is, right? The length of the tent peg. Just like this was the length of the rope from A to B. Or 0.42. Pardon?
0.42.
142? Okay. So now, if we want to take the dot product of the two vectors, tell me what to write. Help me out. D to B. What should I write out for these?
Z.
What's that?
0.08 times 3, or negative 3?
Negative 0.08.
I'm sorry, negative 0.08 times negative 3.
Good. Plus what?
3 times 0.38.
Let's keep the same order. 0.38
Okay,
times
sorry.
3 plus the last term.
0.16
Good.
times negative 1.5.
That's right. That's it. So there's the dot product on the left-hand side of the equation.
It won't matter since you're swearing.
Guys, you're welcome to whisper, please. Whisper. And if we take the multiplication of the two magnitudes, well, D with respect to B is 0.42 meters. And the other one, the magnitude A.
Negative.
4.5.
Yes, please do whisper.
Put parentheses around it.
Excuse me, please do whisper. AB, 4.5 meters. And that's cosine of the angle between the two. Now what about on the left-hand side? What are the units over here? Well, they're just meters squared, aren't they? Because each one of these have units of meters, we're adding meters squared together, and we have meters squared on this side, so everything makes sense. So all our units go away nicely. And now all we need to do is take, let's compute this number. So what is the dot product on the left side? Anybody calculate it by now?
I'm not getting .42 for
The magnitude?
DT, yeah.
What are you getting?
We're having conflicting answers.
Yeah, I mean, I
What
got
answer?
16 twice,
You got 16?
yeah, so.
There's no way you're gonna get 16 from that. And that's 16 meters. What numbers are you typing in?
Negative .08
And then squaring it?
plus .32 or .38
0.38 squared?
And then 16 squared,
You mean 0.16 squared?
yeah.
And then you take the square root?
0.14.
Yeah, there's no way it's that large. There's just something with your calculator you're not doing right. You can see from the magnitude of these things that you're gonna get something on the order of point something.
I'm not including parentheses. I think when you include parentheses on calculators or like the minus signs, it like messing up, cause he got .42 and I got .40, like 404, and then he just got .389.
I got .100.
I got 14.
Well, I'll bring up the calculator and we'll figure it out. Let's see. I'm glad you brought it up though, because I want to make sure we get the right answer here. All right, so did you know that the calculator included with Windows actually has a programmer and a scientific one? It's really handy. So I'm going to take .08 squared, add to it .38 squared, add to that .16 squared, and the result is .1764. Does that make sense? Yeah. And then I'll take that result, take the square root of it, I get .42. So .42 is the right number.
I think it might have been my parentheses.
Okay. Thank you for bringing it up, because if you're having trouble, so are other people, so that's a good thing. And that's the kind of thing where if you get stuck on it, you won't follow the rest of the example problem, so always feel free to bring it up, that's good. So why don't we calculate then, let's just divide this by .42 and also divide it by 4.5, that'll get rid of them from that side. So what do we get for the cosine of the angle?
0.603.
Notice that for the cosine of anything, you should get a number less than 1, right? Or greater than -1. Because cosine, the function, always returns a number between -1 and 1. So if you ever calculate a dot product and you're over here and you get some number greater than 1 or less than -1, you've done something wrong over here. Okay? Because you can't take the inverse cosine of, say, -2. It doesn't work. You can't take the cosine of 2, or the inverse cosine of 2 either, because there's no such thing. So let's take the inverse cosine of .603 and see what angle there is between these two vectors. Or between the tent peg and the line. So from this dot product, essentially, theta is equal to what angle? .91. Anybody agree? So there's the angle between the two. But part B says, what's the projection on the stake of the force exerted by rope AB at point B? Do they tell us? Yeah, there's 540 newtons pulling. So couldn't we write down the vector, the force vector, along rope B to A, or AB? I think we could. Let me do something. Let me erase this magnitude. We may need the magnitude later, so let me just make a note. 0.42 meters, so I don't forget. And then over here, 4.5 meters. And let's see, we got the angle between the two. Let's make a note of that. Theta is 52.91 degrees. And we'll get some space so that we can do a little more work. Why would we care about the projection of the force in the rope along the tent peg? Why would that be useful at all? Doesn't that tell you how much rope AB is tending to try to pull the tent peg out of the ground? Yeah, so that's actually a pretty interesting thing, because then we know how much force the tent peg actually has to how much force the ground has to apply to the tent peg to hold it in the ground. So this projection is actually really interesting. So I think what we ought to do is try to write the force vector F. Now we know the magnitude of the force vector is 540 newtons. That was given in the problem statement. Excuse me. And we also know that this force vector acts along rope AB. Okay, or BA. So could we write down the magnitude or the force vector itself as a vector? Well, sure. All we need is the vector from B to A, which we've got, and then we need to turn it into a unit vector. In other words, we need to multiply the magnitude of the force, which is just another way of writing this, right, times the unit vector lambda that points in the direction B to A, or in your book's terminology, 2A from B, A with respect to B. So what do I mean by this unit vector? Well, what I mean is we ought to take this position vector, divide it by the magnitude, which is 4.5. Of course, we've got meters over meters, so this is a dimensionless thing. It'll have unity length. It'll have length 1. And that'll give us a vector that just points from B to A. Right? And that will allow us to write down the force that points from B to A. Okay? So let's do that. What do we get? So negative 3 over 4.5 is what? What is that?
Negative 0.6 repeating.
0.6? Oh, yes, okay. We'll have a similar number here, positive 0.6j repeating. And this the line above the 6 is not indicating that 6 is a vector, it's just indicating that it repeats over and over. And then finally we'd have what, negative a third? So 0.3 repeating. And this is now dimensionless because we had meters over meters, so they just cancel. So there's a unit vector in the direction from B to A. So the force vector then would be 540 newtons multiplied by all this. So now I need you to multiply 540 by 0.6, for example. What do we get? Well, 0.6 repeating. So what is 2/3 of 540?
360.
360. So negative 360 newtons in the I direction, plus 360 newtons in the J direction, and then half of that minus 180 newtons in the K direction. Now these are all newtons of force. Okay. So now what we can do, if we want to know how much of force F acts along the stake BA, we just need a unit vector from B to A, take the dot product of the unit vector with the force vector F, I'm sorry, not B to A, B to D. And that'll tell us how much of force F acts. Sorry, I'm forgetting my dash is above the unit vector to indicate that it is a vector. This will tell us how much of force F acts along the tent peg and tends to pull it out of the ground. So it looks like we need another unit vector, and that's from this other vector over here. So in other words, the unit vector from B to D would be equal to negative 0.08I plus 0.38J plus 0.16K divided by 0.42. So meters again over meters, they cancel, and we've got a unit vector then from B to D along the tent peg. Okay? So go ahead and do the calculation, if you will. What is 0.08 over 0.42? That should be 8 over 42, which I think would be 0.6, isn't it? No. It's just 6. That doesn't make sense. It's less than that. What is 0.08 over 0.42?
0.19047.
Why did I think it would be 0.6? Oh well.
Or, yeah, negative.
Wait a sec, that doesn't make sense to me.
That's what I got.
Oh, 6/8 are 48. Okay, I'm sorry, what's the number again?
0.190.
190, thank you, in the I direction. How about 0.38 over 0.42?
Um,
0.905.
yep.
And the K direction, 0.16 over 0.42?
0.381.
Yeah.
Okay, yeah, I'm not thinking right. I'm with you now. So there's our unit vector from B to D. And so now all we have to do is take the dot product of the force vector with that direction vector, that direction unit vector, and we'll have it. So we need negative 360, of course these would be newtons, times negative 0.19, which are dimensionless. I'll make it 190 just to be clear. Plus 360 multiplied by 0.905 plus, well, plus negative 180 multiplied by 0.381. All these are newtons and then non-dimensional, so we'll just get newtons of force. So go ahead and calculate this for me if you would, please. And this will tell us how much force is trying to pull the stake out of the ground. Let's see, that's about 20%. So 72. 60.
325.62.
That's what I got. How much?
325.62.
0.62?
Uh-huh.
So 326 or so? Yes. So there's the force trying to pull that tent peg out of the ground. If the ground can't apply that much force on the tent peg comes out of the ground. Very simple. Okay. Any questions about this problem? All right.
What's the difference between the big dot and the small dot again?
What's that?
The difference between
The big what?
dot product versus multiplication?
Yeah, I'm not doing a good job of using big and small dots, but that would be multiplication. How do I know? Because that's a scalar. The only time you can take a dot product is when you have two vectors. So you pretty much have to tell from the context whether it's a dot product or multiplication, because if it's two vectors, you can't multiply. If it's a scalar and a vector, you can't dot product.
Coolio.
All right? Good question. Anything else? Alright,